Our story begins in the vast expanse of the Milky Way galaxy. Imagine a swirling mass of stars, gas, and dust, a cosmic ballet billions of years in the making. A collision with a dwarf galaxy set the stage for our solar system's formation. This collision sent shockwaves through the Milky Way's interstellar medium. These shockwaves compressed clouds of hydrogen and helium, causing them to collapse. As these clouds collapsed, they formed rotating disks of material. At the heart of one such disk, our sun was born. The sun's gravity drew in surrounding gas and dust, forming a swirling disk of debris. This debris eventually coalesced to form the planets, moons, and asteroids of our solar system. In the swirling disk of dust and gas surrounding the newborn sun, a new chapter began: the formation of Earth. Imagine a chaotic scene, a cosmic shooting gallery where tiny particles of rock and ice called planetesimals collided and stuck together. Over millions of years, these collisions grew more frequent and more intense. Planetesimals, drawn together by gravity, smashed into each other, generating immense heat. The energy released in these collisions melted the accumulating mass, creating a planet-sized ball of molten rock. This molten Earth was a scene of intense volcanic activity, spewing lava and gases into the surrounding space. As Earth cooled, heavier elements like iron and nickel sank towards the center, forming the planet's core. Lighter elements, like silicon and oxygen, rose to the surface, eventually solidifying to form the Earth's crust. This process of differentiation, driven by gravity and heat, laid the foundation for our planet's layered structure. The early Earth was a far cry from the hospitable planet we know today. It was a violent and volatile place, bombarded by asteroids and comets, its surface a sea of molten rock. Yet, from this chaos, order would emerge, and the stage would be set for the next chapter in Earth's epic journey. As Earth continued to cool and solidify, a dramatic event occurred that would shape its destiny: a collision with a Mars-sized object. This cataclysmic impact, known as the Giant Impact Hypothesis, blasted a significant portion of Earth's mantle into space. The debris from this collision, a mixture of molten rock and vaporized material, didn't simply drift away. Instead, it was caught in Earth's gravitational pull and began to orbit our planet. Over time, this debris coalesced, drawn together by gravity, to form the Moon. The Moon's formation had a profound impact on Earth. Its gravitational pull stabilized Earth's rotation, preventing extreme wobbles that could have led to drastic climate swings. This stability was crucial for the development of life. Furthermore, the Moon's gravity created tides, rhythmic rises and falls in Earth's oceans. These tides, along with the Moon's role in regulating Earth's axial tilt, played a crucial role in shaping Earth's climate and influencing the evolution of life. The Moon, our constant companion in the vastness of space, is a silent testament to the violent events that shaped our early solar system. It's a reminder that even catastrophic events can have unexpected and ultimately beneficial consequences. The early Earth's atmosphere was a far cry from the life-sustaining blanket of gases we breathe today. It was a toxic mix of carbon dioxide, nitrogen, water vapor, and other volcanic gases spewed out from the planet's molten interior. This early atmosphere lacked free oxygen, the gas essential for most life as we know it. Over time, Earth began to cool, and the water vapor in the atmosphere condensed to form the first oceans. These early oceans were acidic and filled with dissolved minerals, a stark contrast to the salty waters we're familiar with today. The transformation of Earth's atmosphere from a toxic haze to a life-sustaining environment was a gradual process, driven by a combination of factors. Volcanic eruptions continued to release gases from the Earth's interior, while asteroid and comet impacts delivered water and other volatile compounds. A key turning point in the evolution of Earth's atmosphere was the emergence of life itself. Early life forms, simple single-celled organisms, played a crucial role in shaping the planet's atmosphere, paving the way for the evolution of more complex life forms, including ourselves. Section 5. The Rise of Life, a delicate balance of elements and energy. Life on Earth showcases matter's ability to self-organize into complex systems. Life's origins remain a mystery, driven by energy and chemistry. Early Earth was a chaotic world of volcanic activity and lightning storms. Simple organic molecules formed in the primordial soup. These molecules became amino acids and nucleotides. They combined to form proteins and nucleic acids. RNA, crucial for life, stored genetic information and catalyzed reactions. RNA likely predated DNA as the genetic carrier. Early life forms were simple prokaryotes. They were anaerobic, not requiring oxygen. Oxygen was toxic to these early life forms. Section 6. From single cells to complex organisms, the dawn of eukaryotes. For billions of years, life on Earth was dominated by prokaryotes, simple single-celled organisms that lacked a membrane-bound nucleus. However, around 2 billion years ago, a profound shift occurred, the emergence of eukaryotes. Eukaryotic cells are characterized by their complex internal structure, including a nucleus that houses their DNA. They are also much larger than prokaryotes. The evolution of eukaryotes was a major turning point in the history of life, paving the way for the evolution of multicellular organisms. The prevailing theory for the origin of eukaryotes is endosymbiosis. This theory proposes that a prokaryotic cell engulfed another prokaryotic cell, but instead of digesting it, the two cells formed a symbiotic relationship. The engulfed cell, capable of using oxygen to generate energy, eventually evolved into the mitochondria, the powerhouse of eukaryotic cells. Another endosymbiotic event is thought to have given rise to chloroplasts, the organelles responsible for photosynthesis in plants and algae. The evolution of eukaryotes was a major leap in complexity. It led to a dramatic increase in the diversity of life on Earth, setting the stage for the evolution of plants, animals, and fungi. Section 7. Shifting continents, evolving life. The dance of plate tectonics. Beneath Earth's surface, a slow and powerful dance has been going on for billions of years. Plate tectonics. This movement of Earth's lithosphere shapes continents, oceans, and life. Imagine Earth's surface as a giant jigsaw puzzle, with massive plates constantly shifting. These plates collide, pull apart, or grind, creating mountains, volcanoes, and earthquakes. The formation and breakup of supercontinents have played a significant role in Earth's history. The dance of plate tectonics is a constant reminder that Earth is dynamic and ever-changing. Section 8. An explosion of life, the Cambrian period and beyond. The Cambrian period, which began about 541 million years ago, marks a pivotal chapter in the history of life on Earth. During this time, known as the Cambrian explosion, there was an unprecedented burst of evolutionary innovation, a dramatic increase in the diversity and complexity of life. Imagine the oceans teeming with a bewildering array of new creatures, trilobites with their segmented bodies and compound eyes, bizarre-looking invertebrates like Hallucigenia with its spiky spines, and the first predators such as Anomalocaris with its formidable grasping appendages. The Cambrian explosion wasn't a single event, but rather a period of rapid diversification that lasted for millions of years. Scientists believe that a combination of factors contributed to this remarkable surge in evolution, including rising oxygen levels, the evolution of new body plans, and increased ecological interactions. The Cambrian explosion marked the beginning of the Paleozoic era, a time of dramatic changes in Earth's history and the evolution of life. During this era, plants colonized land, fish evolved jaws and fins, and the first amphibians crawled out of the water, paving the way for the colonization of land by vertebrates. Section 9. From primates to humanity, a journey of intelligence and innovation. The story of human evolution is a long and complex one, spanning millions of years and encompassing a diverse array of ancestral species. Our journey began in the trees of Africa, where our primate ancestors evolved grasping hands, binocular vision, and large brains. About 6 million years ago, a lineage of apes diverged, leading to the evolution of humans on one branch and chimpanzees and bonobos on the other. Our early hominid ancestors, such as Ardipithecus ramidus and Australopithecus afarensis, walked upright but still possessed small brains. The genus Homo, to which modern humans belong, emerged around 2.8 million years ago. Homo habilis, known for its use of tools, was followed by Homo erectus, a species that mastered fire and migrated out of Africa, spreading across Asia and Europe. Homo sapiens, our species, emerged in Africa around 300,000 years ago. We are characterized by our large brains, complex language, and capacity for abstract thought, art, and culture. Our species has spread across the globe, adapting to diverse environments and leaving an indelible mark on the planet. Section 10. A Future Unwritten: Challenges and Opportunities for Humanity. As we stand at the precipice of the future, humanity faces a multitude of challenges and opportunities. Our actions in the coming decades will determine the fate of our species and the planet we call home. Climate change, driven by our reliance on fossil fuels, poses an existential threat to our civilization. Rising sea levels, extreme weather events, and mass extinctions are just some of the consequences we face if we fail to address this urgent issue. Resource depletion, pollution, and overpopulation further exacerbate the challenges we face. However, amidst these challenges lie incredible opportunities for innovation and collaboration. Advances in renewable energy, sustainable agriculture, and space exploration offer hope for a more sustainable future. Artificial intelligence, biotechnology, and nanotechnology hold the potential to revolutionize medicine, energy production, and economies. The future remains unwritten. It is up to us, the inheritors of billions of years of cosmic evolution, to choose our path. Will we succumb to the or will we rise to it? Harnessing our collective intelligence and ingenuity to create a brighter future for all. The choice is ours to make.